Okay, looks like it started. Okay, so thank you everyone for coming. So we're staying in the, I guess, kind of compiler vibes for this talk and the next few ones. And so this week we have Mathieu from the University of Cambridge, and I guess Edinburgh. I'm not like before that. He's going to talk to us about an SMT dialect for MLIR. So I guess, yeah, Mathieu is in Cambridge with Tiberius Gross's group, same as Louisa, who was presenting last week, and has been working on this. And now more recently, I guess, Fehr, which is a formalization of MLIR in Lean. And so I'll let you take it from there.
Yep. Hi, everyone. So I'm Mathieu, and today I'm going to present you this kind of formal semantics for MLIR dialects as dialects. So this is a joint work with some people at the University of Utah, Hugo Popuniak, who was visiting us, who's from INRIA, I think, and was visiting us at the time in University of Cambridge. And yeah, so the main thing is compilers are kind of complex. Like I kind of all know about this for now. Like if you look just at LLVM, this is like a huge beast of like a project, and there's many things going on at the same time. And that means there's a lot of bugs. And to the point that there's an entire field that's just dedicated in like academia to just find bugs. So the number of bugs is, however, not going very down. The number of bugs seems to be a bit going up. And the idea is, how do you catch them? How do you make sure that they don't even like appear in the first place? How do you make sure that whenever someone like put a pull request, you are sure that there's like no bug in, let's say, compilers when you have to do a rewrite, when you have to implement like some passes. So the way in LLVM you would prevent miscompilation, so you take an input and an output program. So here it's like the difference between doing, let's say, x times y times z in LLVM and x times y times z with the flag NSW, which is essentially saying that if there's an overflow, then that means we have what's called poison. So if you have this rewrite, the way you would do it in LLVM is you would pass it to the tool called alive. So alive is just an automatic tool that essentially is going to tell you if whatever you're doing is correct or not. Is the input program and the output program like have a valid relation called refinement? And in that case, for instance, it would tell you, no, associativity is actually not correct in LLVM because of this following reason. If you had x equals 0, y equal 100, z equal 100, then your input would have been 0. In your input program would always return you 0, and the output program would return you what's called poison, which is, again, one of the small difficulties in kind of LLVM semantics of like what happens when you have overflows and these kind of things. By the way, if you remove this flag and you have normal multiplication, of course, this is like correct on like normal integers and bit vectors. So alive is very widely adopted in the LLVM community. If we have like, there's thousands of references to it. If you look at the pull request, quite often, if you want to add, let's say, a new rewrite to LLVM, you would just say, hey, look, this is correct. Here's the proof. And the proof would just be essentially a link to the alive website that has, this is the input program, this is the output program, and alive tells you it's correct. So people really like kind of trust it. And it's to the point that if you want to contribute to IntsCombine, which is the instruction combiner pass, which just do this kind of rewrites, then you need to add one of these kind of proof to essentially just not waste either the reviewer time, to just, we know it's correct, and we know there's not going to be any bug. So this works super well for LLVM, which is kind of a closed ecosystem because you have a fixed set of instructions. You always have kind of the same one. And I mean, they're always the same. But in the case of MLIR, which is the case I'm interested in, then we have kind of the same instruction you had in LLVM, but also people added way more dialects that have way more complexities. Like instead of just having arithmetic or like memory, you also have linear algebra. You also have a representation of polynomials. And on top of this, you have all of these other kind of compilers that are built on top of MLIR that also define their own dialects. You have Circuit that represents the comp dialect, for instance. And then you have ARI, you have TensorFlow that all have their own kind of different dialect with their own different semantics. And we can't really have one tool like alive for the entirety of MLIR, because everyone defines things on top of it. So we can't, if you would define, let's say, something like alive for like the MLIR, so there's this project called MLIR TV, which is essentially alive from some subparts of MLIR. If you would want to do the same thing, you would essentially create a duplication of a project. If you would do it, let's say here for circuits, you would have two projects that have to define the semantics of the core MLIR, of the MLIR dialects they care about. They would require the SMT optimization, because just translating, because they all work using SMT solvers. So if you would just translate it directly to SMT, would not be fast enough. So you need optimization. You need a lot of essentially tooling. You need to have all the front end, all this kind of stuff. It would essentially just duplicate everything if we would just decide to just build a life or fixed set of dialects. So what I'm kind of proposing here with what we call these semantics dialects is essentially the idea that you would have a target dialect, a target set of dialects, and you would do essentially a compilation pass from your the dialects you care about to this target semantics dialect. So here, for instance, you would go from what I call the MLIR core, so the dialects in MLIR, or you would go to from circuits, compile down to this kind of first-class semantics in MLIR. Then you would do some progressive kind of semantics optimization. So like a compiler, you would have high-level dialect, low-level dialects that you would compile from the high level to the low level, do optimization at each level like you would do in MLIR. And then you would, from kind of this thing, you kind of build tools around it. One for, let's say, translation validation, so checking that the program was well compiled. One for people rewrite verifier, which essentially checks that a rewrite is always correct for whatever input you have. Or, for instance, it's now a bit used for bounded model checking, so just like checking the program is correct after a certain number of iterations, because you have loops and it's a bit harder to prove that it's always correct. So all of this, I want this to be in MLIR. I mean, we're building this in MLIR, so everything is kind of MLIR dialect, MLIR pass, all these kind of things. And one of the main goals of saying that kind of semantics in the compiler here is that we can have three kind of experts that have a separation of concern. So while before in a live, you need someone that is able to understand the LLVM compiler, be able to understand SMT, because all this optimization, and need to be just kind of build a tool around it. Here we can have like two different separation of concern for like three experts, where you have one person that's taking care of saying what is the semantic of my compiler. So what do we compile, let's say, an arith add to? One which is understanding, an expert on SMT, if you have certain, like what kind of optimization you can write on your SMT abstraction, on your semantics abstraction to make this more amenable for SMT solver. And one which is just, yeah, what kind of tools we want to build around it. So let's look a bit kind of what that means when I say like we want to compile to first-class semantics. So currently in Alive, if you want to do, let's say, translation validation, so checking that the program was correctly compiled, let's say you have division by 8, sign division by 8, that you compile to a shift by 3. The way Alive would do it is it would compile it, I mean, it would translate it to SMT expression. So instead of a division by 8, you would have like the equivalent in the SMT language called SMTlib by 8. You would have a shift by 3, and then it would kind of combine these expression and then check if these expressions are correct or not. That's the role of the SMT solver. So the thing is, when you look at it that way, this looks a lot like kind of an intermediate representation. If you have the LLVM code on the top, the SMT code on the bottom, you can think that what if we make kind of SMT a dialect here? And that's where we kind of started with. So if you look at SMTlib, you can easily translate it to an MLIR dialect, because essentially SMTlib is based on Lisp. So this is a very like kind of functional programming style of writing expressions, and that's very amenable to translate it to SSA. So we just took the kind of SMTlib reference, and then we just translated it to an MLIR dialect, and we have translation to go from SMTlib to the SMT dialect. So that allows us to kind of interact with the SMT solver because we can now write programs that can be used by SMT solver. So now if we want to give semantics to, let's say, the arif division or the arif shift, like we had for LLVM before, well, we just use a compilation pass. So now defining semantics for a dialect, defining kind of the meaning of what a dialect is just using a compilation pass. And so we started this by defining kind of dialects for arithmetic, memory, SCF, comp, and we compile it to the different kind of flavors of SMT-lib. So SMT-lib has this kind of core theory to say the basic things like booleans, checking if there exists, existentials, quantifiers, all this kind of stuff. But they also have theories for bit vectors, theories for array, theories for data types, theory for integers, unbounded integers. And we can already define like kind of a lot of semantics, but there's also like more complexity. Like how do you actually represent what memory is? How do you translate, let's say, a memory read to SMT? So those things are kind of complex, and there's been like a lot of work made by Nuno in Alive to do this. But the kind of idea we had was, what if we have this kind of higher level abstraction like you would always do in MLIR? What if you have this one high level abstraction to define memory effects, one thing we call memory, and also undefined behavior? We added the same for poison, all these kind of things. It's like, what if the target for semantics is a bit more high level than just SMT, which is still a very low level thing? So we added all of these dialects, and that allows us to represent things, let's say, writing 42 in memory in a bit more high level way. So we have things like definition of pointers for memory. We have here like just taking essentially as input a pointer and then having an effect, having an operation in our MLIR dialect, which is just taking the offset of a pointer. We have similarly what we call state. Essentially, it's the state of memory, the state of the world in some sense. And then we can just write in that state, and then we can read. We can trigger undefined behavior as well with it. And as the idea of kind of capturing all side effects and all kind of corner cases you can have whenever you deal with memory, because you can decide to not have undefined behavior. Let's say if you write outside of the places you are, you can decide to have, you can have essentially a lot of like, this is a way to represent in kind of a lower level what memory does without going too low level into SMT. So with that, we can define semantics of MLIR. So we can just take MLIR dialect, we write a compilation pass, and then we get our semantics kind of target. So then from this, we want to do some optimization, because, and that's the role kind of the SMT expert. Because the idea is, once you have this kind of high-level semantics, like the memory effect or memory, we want to still be able to target SMT-lib, because that's essentially the way we can check if it's correct or not. That's where we can then pass it to the SMT solver, and the SMT solver is going to have the role of checking if like the program was correctly compiled, this kind of stuff. So for that, for compiling essentially everything, we need to define kind of what memory, how to represent it in SMT. So we base this work on kind of what, as I said before, like how Nuno does it for Alive. Essentially, it's a representation of memory. That's the LLVM kind of encoding of memory in SMT. And we essentially just follow that, but by making it a dialect. So while Nuno had it, essentially he was writing optimization, at the same time he had his translation to SMT. We have kind of a one-step translation to the memory, and then one part which is optimization directly on this dialect. One kind of other optimization we can do is not necessarily on the memory by the lowering, but we can also have like optimization directly on SMT-lib itself. So if we take, for instance, just something that defines a function that takes as input a pair, we can just kind of compile it or have a better encoding of it by just saying we have a function that takes two inputs. And if we say, oh, we have a function that returns a pair, then we can just say instead we have two functions. And while this might seem a bit weird on like traditional, let's say, compiler, you would never usually translate a function returning a pair by two functions. Well, in our case, it had actually speedups by just doing this kind of optimizations. Whenever we had an SMT query, we had like a 60% speed up with Z3 on our example, which used a lot of these pairs. And this was because probably Z3 did not have the right kind of optimization in itself. So by writing it as a compiler, essentially we are able to add new optimization to the SMT solvers. So we tried it for Z3, we had some speed ups and we reduced the amount of timeouts we had. And when we did it for CVC5, we had no changes because this was actually implemented by CVC5. But that was kind of an interesting like insight that like we can kind of write optimization to make SMT queries kind of faster on certain SMT solvers. So once we have this kind of pipeline, we can go from our MLIR code to SMT. Now we can kind of build tools for it. And I have kind of example of 3 tools that we've built around this kind of SMT representation in MLIR. So we have translation validation, we have checking that the program was correctly compiled. We have pass verification, checking that a pass is kind of always correct, that there's no bug in a pass, and data flow verification. So checking that data flow analysis or abstract interpretation is correct here. So for translation validation, we take, let's say, a program in Arif. We want to show that it was correctly compiled to an Arif program. We can also do it for other dialects. We can say that an Arif program was correctly compiled to an SMT program, let's say. So we take both programs, the input-output program, we compile it to our semantics dialect, and this is kind of a reusable component, just like compiling it. And then after that, we just do semantics optimization on kind of the combination of these 2 programs, and we check that one refines the other, like one is equal to the other. So we did that. We had like a small tool. It's not very complex to write. And we run it. It was, I think, a year or 2 ago on MLIR. And we found a few bugs, actually. So surprisingly, in, let's say, it was the arithmetic dialect. So there was like 5 rewrites that were incorrect in the arithmetic rewrites. So here, this is just the first. Essentially, they were all using the what's called arith.select operation, which is just an if-else. And the problem was that there's some rules related to poison, which were here not respected. So all of these had a bug in the case where pred A or pred B had poison. So I'm not going to go too much in detail on it, but essentially the way poison is propagated in select is a bit different than other operation. You can have one input being poison, and yet the result is not poison. So we kind of find 5 bugs. Recently, a month ago, there was another few set of bugs that existed in Arif that we could kind of reproduce with our tool, and just like fuzzing it again, we could like find again new bugs that appeared in MLIR since then. So that was for translation validation. Now we have people rewrite verification. So this is essentially checking that people rewrite in the compiler is always correct. So for that, we use PDL. So PDL is an MLIR dialect to represent rewrite. So it's a bit meta, but it's like that way you can kind of combine rewrites and make things a bit faster than if you would write it in C++, for instance. And we take PDL, we compile it to our semantics dialect. So we take an MLIR program representing a rewrite, and we represent what this rewrite means in terms of our semantics dialect using the kind of semantics of the general MLIR dialect. So if you have a PDL rewrite on Arif, we kind of use a compilation pass inside our compilation pass to say what it means using the Arif semantics. And then we do some optimization. So if you take like a small example, I think this is a rewrite that just do commutativity. So this is a PDL rewrite. So we match type that is I32. We match two operands of type I32, so X and Y. Then we match an operation that is just X plus Y, and we say that we're gonna rewrite it with Y plus X. So we just replace X plus Y with Y plus X on I32. The way we compile it in kind of our semantics dialect or SMT-lib in that case is we just say we declare two values. We say we have X and Y, which has two values. We compile using kind of a compilation pass inside it. We say that arif.add, we know it's equivalent to an smt.bv.add. So this is like translating this operation to SMT-lib. We do the same for the operation we're creating. And because we're replacing one with the other, we just check that here they're different. So here, this is a very like simple verification where we just check that they're equal. But in practice, you can do more things, like if the input is poison, you can have concrete value as the result. So yeah, and then we just have an SMT assert is just essentially checking that one is equal to the other. And then we pass it to the SMT solver. It's going to say that the rewrite is correct. So we went over and we took the SMT. So at the time I was writing it by hand, but essentially converting the arithmetic canonicalization pattern from MLIR to PDL. And then we launched kind of this PDL verifier, just verifying people rewrites in our tool. So it found, again, the 5 bugs that we found before. And here, essentially, we checked up to 32 bits or 64 bits, integers, I forgot, that essentially all these rewrites are correct. So it took a bit of time for some of the rewrites. I think it was like 200 seconds to prove that some rewrites are correct, because they match on 3 different types, and you need to enumerate all of them to 32 bits. So you have essentially to enumerate 32 to the power of 3 rewrites. And once this has been verified, that means that these rewrites are always correct. And in particular, that means that the arif canonicalized pass will always be correct and have no miscompilation, because we proved that it's correct on like kind of all inputs, up to 64 bits, of course. So that was kind of like the second tool proving PDL rewrite. So lastly, the third tool we have is data flow analysis, so verification. So data flow analysis is, or what you can call also abstract interpretation, is just having like an analysis on program that tells you what kind of values certain variables in your program can have. I'm going to go a bit in detail on this. So if we take, let's say, a comb or like an arif dialect, we write our transfer function, so our data flow analysis, in MLIR as well, using kind of our new dialects. And then we can just compile them to their semantics counterpart, and then we check that they're kind of match. So data flow analysis, like a simple example of what we can have, is what's called non-bits analysis. This is something that's heavily used by LLVM and extremely important for its performance. It's the idea that for each variable, you check for each bit statically, is it always going to be 0? Is it always going to be 1? Or is it going to be unknown? And that means for a particular, let's say, variable, if, let's say, the analysis tells you 1, 0, question mark, that means it can have 4 different values, where the first one is a 1, the second one is a 0, and then the third and the fourth one is unknown. And the way you compute this kind of analysis is if you have here an arif.end that takes an input of variable, which was just taken as the input of a function, and the second input is the constant 1. Then we have the variable is unknown, in the sense that we don't know the value of any bit. The C1 variable is essentially 0001. And if you want to compute the result of this operation, well, you need to call what's called a transfer function, which is going to take as input the operation you have, and it's just going to return you the right computation for ni, which is here, or I didn't write it, which is just 000 question mark. So here you know that if you have a variable that's unknown, you do an end with 1, then you know essentially only the last bit might have a value, the rest is necessarily 0. So this transfer function is essentially the core of this kind of algorithm, or the core of this analysis path. And this is the thing we essentially translate, which is a write as MLIR programs. So we added kind of, well, I didn't show it here, but we added a transfer dialect in MLIR that's essentially represent these kind of transfer functions, and you can write, we can add things like AP ints like you would have in in C++ MLIR. Essentially, we write like kind of a nice MLIR dialect API to just be able to write these transfer functions. And here for the end, for instance, the way it works is that there's a few variables you have to manipulate, because all of these non-bits are represented using 2 integers, and then you manipulate these integers to return the result. And from this kind of way of representing data flow function, which is essentially the same way as in C++ with MLIR, you can check if it's correct or not. Essentially, if your analysis was correct, you can check if it was precise. So essentially, is your analysis the best it can be? Which is often the case for things like AND and OR, but for things like multiplication, it's like really hard to have something that is precise. And you can also compile it to a C++ program. So whenever you have this kind of analysis written in MLIR, you can directly compile them to C++, and then you have kind of efficient implementation, the same way you would have C++, but at least you can check it if it was correct or not. And we use this to kind of build a better data flow analysis in COMB. So COMB being the combinatorial dialect in circuit for hardware synthesis. And essentially, so one take was us having like a verified implementation, and the two takes having a precise implementation, saying the best implementation you can have, at least in terms of like, I mean, not in terms of performance, in terms of precision. So checking that the result is as precise as it can be. So we just like kind of improved the one we have in circuit. We did it for non-bits, and we also added an implementation of demanded bits, which is not checking what's the value of a bit, but instead it is checking if a bit is actually used in the program or not, which also allows you to write some interesting optimization. So all of these are kind of like checked by ours, and because we can kind of check it, it's kind of easier. Our claim is it's kind of easier to have, let's say, more strong data flow analysis, because we can at least prove that it's correct or not. Whereas if you have like complex data flow analysis, I mean, complex transfer function, it's kind of hard to say, oh, is this actually going to be correct or not? So this is kind of like the 3 tools we built. There's another one I haven't mentioned here, but we were working on super optimization and synthesis of rewrites as well, and lowerings. There's something that was still like kind of ongoing, and we had some kind of interesting results. And the main idea is that we kind of use this PDL verification or this translation validation to check that the super optimizer we've written is correct. So in conclusion, we kind of added this first-class semantics dialect to MLIR. So the idea is that we had SMT-lib, and then on top of it, we had our high-level dialects to represent things like memory or poison or undefined behavior. We use this so then we can map MLIR dialects from either the core of MLIR or from the kind of more global ecosystem to it. And we define kind of optimization in a way, I mean, as a compiler pass, which allows you to kind of have this layer separation with the people that define the semantics of the program. And all of this is in MLIR. Technically, it's in XDSL, which is kind of a Python implementation of it, but some of the SMT dialects are now used in MLIR and have been used by other people. And we use this to build kind of these 3 tools: translation validation, a people rewrite verifier. And I think the bounded model checking is what people have been doing in the circuit community so far. And yeah, we have kind of 2 more separation of concern, which allows you hopefully to build like better tools for it. And thanks.
Thank you. Very, very cool. I have one initial question, I guess. which is when you plug in Z3, and I don't know if you've plugged in also CVC5 or the SMT solvers and how much effort that would be compared to plugging in Z3, but I'm also curious whether there's any serious engineering work that's required to make it work for specific decision procedures inside the SMT solver, or whether it kind of works in a fairly natural way.
So there's a good and a bad thing. So the good thing is that we used SMTlib. So the idea is that we just like an input file that you can pass directly to Z3, you can pass to CVC5 and all that stuff. So that means that adding a new SMT solver, if it has SMTlib support, that's fine. Which I believe at the time Bitvuzla was not, or there was like an SMT solver wanted to try, it was not working. The problem by doing this is that you essentially need to write in a file. And in the case where we used it in a super optimizer, this was actually too slow because we just kept having relaunching new Z3. So having like just a CLI for this was much better, but it was not substantial engineering work. It's just like mapping essentially each operation we have, mapping it to what would be the SMT call for it, the Z3 call for it. There was one issue, though, is that SMT solvers, though they have kind of this SMTlib specification that they kind of respect, a lot of them has additional things that's not necessarily documented, but that's all very useful to have. For instance, in Z3, you can have checking if a multiplication had an overflow and add an overflow. This is something we used a lot, but this is something that's only available in Z3 and not in CVC5. So what we had to do is whenever we use this kind of optimization, we will need to add a new compilation path to compile this instruction to things that other SMT solvers can accept.
Yep, that makes sense. Yeah, I think there's some analogous things in proof of systems as well, where I think if you want to access, I think this was in Isabelle, to get access to better results from the floating point decision procedures in, I guess, Z3, they had to then formalize that floating point stuff in Isabelle first, and then do an SMTlib encoding of that, rather than just passing off kind of problems in a more naive way. So also, this is similar.
Yeah, we haven't really tried all the Z3 tactics kind of thing, or even setting the theory in general, because Z3 usually kind of detects that. Because we've mostly been using it with just bit vector or bit vector plus array, Z3 would just detect the right theory. So we didn't have this problem, at least. But I guess if you're using like some kind of weirder theory, maybe it's not auto-detected, these kind of things.
I think, yeah, weirder theory might be an issue. And then also if you do combination of series that are required within a dialect, then maybe you would have issues as well. But that is probably better avoided by designing your dialects in such a way that they don't need combinations of series, which is maybe a fairly natural thing to do in MLIR anyway.
Yeah. Also, yeah, you can set the theory. I think at some point we needed to add this. I forgot why, but you can set the theory directly in SMTlib. So that's usually fine.
Yeah. Okay. Any other questions from anyone else?
I have one.
Yeah, go ahead.
Hi, thanks a lot for the talk, Matthew. I was just wondering, so you do have these like two separate things in which you can do like optimizations, right? Either on the kind of compiler expert side or on the SMT side. Have you experienced at some point that the compilations on one level were actually kind of breaking away some structure that would have been useful in optimizing the level just below?
So that's a bit yes, in some sense, but that's the kind of idea of, I would say, the general idea of MLIR in some sense, because the point is, if you want to do optimization at the memory level, you stay at the memory level. Oh yeah, but I see what you mean. No, I don't think I had this. So the case where like having an optimization at the memory level breaks the lower level in some sense.
Yeah, it's more like, I don't know, we have been kind of playing a little bit with creating some constraints for like a ZK language. And sometimes there are some, I don't know, information about control flow, for instance, in the higher level language that's broken down when you go to, let's say, opcode level. And having this information there to begin with would have been very helpful, even at the SMT level. but by then we have already lost it. And I was wondering if you had analogous things where maybe some compiler optimization is kind of breaking away some structure that would have been actually quite useful at the SMT level.
I see. Luckily not, but that's also because the amount of optimization we have was literally a bit on the memory side and a bit on this kind of pairs things. And so beside that, we didn't have really like complex optimization. So essentially that was usually fine because it's not that much complex in general.
Great, thanks.
Yeah, thanks.
Okay, anyone else? And otherwise, I have one more on my side, which is that obviously you've worked on this, and then I guess, are currently working quite a bit on Fehr, which I guess we'll have a talk about that in the future. But from the perspective of having worked on both, how would you kind of contrast, I guess, the different use cases for both approaches and how complementary or not complementary they are? Because obviously in Fehr, you might think like, okay, we just clarify the optimization passes in lean, but there might be things for maybe like JIT compilers where you want, I don't know, some SMT stuff at runtime. And I don't know how much you've kind of thought about the combination of both approaches.
Yeah, so there's two things. So just maybe just to remind people, or at least they might not know. So Fehr is kind of our re-implementation of MLI in lean. So essentially the goal is to be able to write a rewrite, to be able to execute it in lean, but also to be able to prove it correct. So one of the main differences is that things like memory, for instance, whenever you compile this to SMT, whenever you want to have an SMT solver solve it, you just give it the input program, the output program, and it's going to find a way to prove this correct or not. Whereas if you want to prove it in lean, you have to kind of think about it. You need to say, oh, this is correct because, and then have manually write it, or have a tactic, or have an LLM do it for you. So in lean, you can represent things in a more high level. You don't have to do this, oh, I need to compile my memory to SMT. You just write an API around memory. You still have to build what memory is in lean, but then you have to just build an API to be able to do proofs about it. And you don't have to always like compile it and do optimization of compilation. This is not something that kind of makes sense. It's just like building API. So you can build better things like you can have like tensor theory, array. Because array theory is a bit limited sometimes when you combine it with other things, but like you can do tensor theory in lean, and you can do like in general proofs of higher level things. The main difference is that you have to manually do it, I think. And when like in this tool, this is like kind of a push button, you give an input. It's like kind of an MLI engineer, I believe, would be willing to just say, if they had a PDL rewrite, put it on a website, press a button like you would do in a live, it tells you if it's correct or not. I don't think the majority of MLI engineer would be willing to just install lean, write their rewrite in lean, check that it's correct in lean, unless it's automatic. And this kind of SMT thing is just trying to build this automation. So in lean, our goal also is to try to kind of automate this, but that's going to be much, much harder than what we did with SMT. And one of the possible goals I have would be to kind of re-implement all the things we've been implementing here, but in lean. So then the idea is that you would also have this kind of automation by using the compiler we're building ourselves. So we would build a compiler, again, like we did with the high level to SMT dialect. We would prove that it is correct. And then that means we can have the same automation, but this time it's verified. Because here, a lot of the code I have still needs to be trusted. If I had a bug in one of my optimization, then that means that we could have miscompilation because of that. So yeah.
Yep, that makes sense. I have some photos, but they're maybe in that sense more related to Fehr in future work. So I'll leave those for the for the Fehr talk in the future. Okay, then does anyone else have any final questions? And then otherwise we can end it here. Okay, then I'll stop the recording and we can end it here. Apologies to every British person for putting this on bank holiday. I didn't realize it was a bank holiday.
I didn't know either. Sorry.
Yeah, the curse of working with international people. But thanks everyone for coming. I guess there's no talk next week, but there will be more talks after that related to MLIR stuff, including one actually on Veridize has an SMT dialect, a Verif dialect as they call it, which will be a nice follow-up to this talk, which should be on, I think, June 1st in a month or so. So hopefully see everyone there, and then in the meantime, I guess everyone can enjoy their day, whether it's a bank holiday or not. So yeah, thanks for coming and take care. And thanks, Mathieu, for the talk, obviously. It was a great talk.
Yeah.
Cheers.
Thanks.
Thanks. See ya.